Stop the recording. Oh, well. So it's now going to be split into two parts. So there's worse things in the world. Okay, so first off, in case you didn't see it, I've been slowly updating our Canvas page, because I guess I should just put some useful information on there, I guess. Okay. Didn't I make a new homepage? Choose homepage. There we go. Save. All right. So now I've changed the homepage. So there, you should be able to see stuff. I've got an email. I've got a link to my email, a playlist of the lectures, and then I've got 2 videos that I watched last night that were suggested for doing RSA. So if you need somebody else other than me to explain RSA, if I've made it too cold and overcompensated, I can change it. This also talks about all the stuff in all the runtimes from our first kind of lecture. But anyway, RSA. So let's get into it. RSA is pretty exciting, in my opinion. It's that whole private-public key idea. So RSA stands for Rivest Shamir Edelman. Even though some stuff there's been like a signature portion using SHA that was deprecated, but the algorithm itself is fine. Okay, so the algorithm itself is fine. The algorithm itself has not been deprecated. I think it was like a specific signature implementation. So RSA is that public-private key that I was going over earlier, okay? And the way it works is that it exploits the fact that doing modular exponentiation, greatest common divisor, and testing for prime numbers, those are all polynomial time algorithms, but factoring a number is exponential time. Factoring numbers is exponential time, figuring out what the factors are. It's just hard. It's just a hard number. So the way it works is first off, what is cryptography, for the love of God? Cryptography is the idea that basically cryptography is the art of making code such that it cannot be, making ciphers, I'm going to be exact with my language. We are making ciphers so that my message cannot be intercepted. This is to distinguish the word cipher from code, which is language that is kind of disguised. Hey, did you deliver Ernie the package? Yeah, I delivered Ernie the package. He's gonna get a nice big surprise. You know, if you've ever watched any mobster movies, you know exactly what the package is here. Okay, so the idea here, that is an example of code, of a code in that context. Cipher is basically turning a message into gibberish, except for the intended recipient. Now, the history of ciphers basically starts with the Caesarian cipher, named after Julius Caesar of the Roman Empire, and the idea, and we name it the Caesarian cipher because that's how it's because that he used it extensively. The idea here is that letters were just shifted. And again, I'm focusing primarily, and unfortunately, all of my education here focuses on things using the Latin alphabet, which is all kind of European history. So I have no idea about how Asian history incorporated ciphers or anything like that. That is actually a subject that probably is worthy of research on its own. But suffice to say, the idea holds that basically we shift things over. So basically, this is a Caesar cipher of 23. So basically, what we do is that anytime we see an A, we move it 23 letters in the alphabet ahead. So it would be X. B gets moved 23 to Y. C gets moved 23 to Z. And what you do is you just simply, to decrypt it, you shift it back. So in this case, the thing you use to encrypt and decrypt are the key. So the key in this case is 23 in the Caesarian cipher. And there's only 25 possible keys that are worthwhile for turning something into gibberish. There's a 26th key, which is move it forward 26 spaces. but that's just going to give you the same, your plain text again. Plain text being the input, ciphertext being your gibberish output, okay? And it does look like gibberish. Now, there's all these fancy statistical analysis that you can do. All languages have like a linguistic fingerprint. So yeah, letter frequency. For instance, English texts will use, E is going to be the most common letter in the id, followed by T, followed by A. These are so basically, if you have a big enough ciphertext and you know that they're using a basic cipher, you can like look at look at the most common thing and say, okay, that's probably an E or a T. It helps, but also like English has this kind of distribution, and those distributions differ based on each language for that uses the Latin alphabet. For instance, the conlang constructed language Esperanto, A appears very frequently as opposed to E. We get a different rank, but more importantly, we've got 12%, whereas Portuguese highest is 14%, English's highest is 12.7%. So there's a lot of different things here. The Veneer cipher took that up a notch and said, rather than doing shifting it by one thing, we're going to shift it by a lot of things. So instead of choosing a key number, we're going to choose a key word. So like if the plain text is, let's see, here's a better one. This is the hello world message, by the way, so this is the hello world equivalent in cryptography, which is attack at dawn. So if your key is lemon, 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 if your key is lemon, you just write down lemon a whole bunch of times until you've written it down once for each letter. And then what you do is you basically do A plus L to get your output, then T plus E, then T plus M. And it works pretty well, but occasionally you get repeated, it has some flaws, repeated keys and the like. Eventually you got to, like over here you can see that the key length is 5. There's a number of things that you do, but that's kind of restricted for security classes. Eventually it got so complicated that we needed machines to do both encryption and decryption. There is only one perfect encryption, and that is called the one-time pad, which basically says that we are going to get I generate a bunch of random numbers, I copy them down once for me, once for you, hand you the pad, and then basically I send you a message and use each number exactly once, and I never and so it's all random, it's all gibberish. Any message I send to you could potentially be decrypted into anything, so you have no idea what's real or not. That is the only theoretically secure kind of way. So that's the ideal, but it's impractical. Now, typically the way we do this is that we do our encryption is using the XOR operator, the exclusive OR bitwise operator, but we're just going to be taking a number and raising it to an exponent here for the purposes of modular exponentiation. For the purposes of RSA. So what the heck is RSA? RSA is that private public key encryption I was talking about. Basically, the idea is that we've got, is that you have some public key, which you share with everybody, okay? And then you've got a private key, which is used to decrypt the public key. So it's kind of a set of locking, it's like a lock and a key, but you can use either one as the lock and then you can use the other one as the key. So if I encrypt it with my public key, it can only be decrypted by my private key. If it's encrypted with my private key, it can only be decrypted with my public key. And we talked about the latter case. That's useful if I wanted to show you that if I wanted to prove a message was sent by me to somebody else, I would sign the message with my private key, and they could only get a meaningful message out by decrypting it with my public key. But more usually what we do is that we use if you want to send me a message, you're going to sign it to me with my public key, and then only I'll be able to decrypt it with my private key. Make sense? So if you want to send me an encrypted message, you use my public key to encrypt it. And the idea here is that nobody is going to be able to decrypt it unless you know my private key. So how does this work? You pick two prime numbers, okay? You pick two random prime numbers, P and Q. And these are going to be really big prime numbers, really, really, really big prime numbers, okay? But for the purpose of all our handwritten examples, we aren't going to go more than 3 digits because that would be insane, okay? And we're going to compute n. Now, capital N over here is going to be the same capital N that we've been dealing with for everything else, which is n is equal to P times Q. Make sense? N is P and Q. Okay? So the public key, then what we need to do is figure out a public key and a private key. Okay? So in order to do that, the first thing we need to calculate is the totient of n. Okay? How many numbers are coprime with n? Okay? And once we do that, and so we pick some e. So here's what we do. Okay, let me go ahead and pull up on the whiteboard. I'm gonna need more space for it. Okay. Okay, and unfortunately the pen has fully stopped working now. So we take P and Q. We take some 2 prime numbers, P and Q. We calculate n is equal to P times Q, and then we need to calculate the totient of n, okay? In other words, the number of numbers that are coprime with this number. We'll leave that for a second. Okay? Then what we need to do is that we need to calculate E. E is going to be used as our public key. Specifically, E and N are used, that's our public key. So how do we calculate that E? E is coprime. E is going to be coprime with N. So we need to choose an E such that the GCD coprime with N of E totient N. So not N, I misspoke there. Totient N is 1. That's what coprime means. The totient, so that's what coprime means. It means that it's equal to 1. Finally, what is the last thing we need? We need a private key. Private key is generated. D is equal to the inverse of D is equal to, well, we need a D such that E times D is congruent to 1 mod totient of n. So that's what we need. We need a D that fulfills that equation. Basically, that basically E times D will give me 1. Now, why is that? Because if I encrypt it, it's just that Caesarean cipher again. Basically, in order to do this, to decrypt a Caesarean cipher, right? If I move it forward by 3 letters, to decrypt it, I need to move it forward by another 23 to do a full rotation. That's what we're doing here. E rotates it a little bit, D rotates it a bit more, so that effectively it rotates fully and we get out our plain number. How does encryption work into this? Encryption works as follows. If I have a message, so what I'm going to do is I'm going to say that I'm going to send a message, any message is going to be some number, okay? And if it's smaller than n, I'm going to split it up into blocks that are each less than n. What I do, though, is I say x, to send a message, I just simply do this. I use my public key to send that message. Now to decrypt that message, I do that, which will fully rotate it. What? Right? Okay, so let's go and fill in some blanks. So first off, let's go ahead and make this a lot easier for us. Calculating that totient is annoying. Fortunately, there's a nice and clean way to calculate the totient. Okay. The nice and clean way to calculate this particular totient is it's just p minus 1 times q minus 1. So in other words, in order to generate, so here's the thing. Why is this hard for somebody to break? Well, we give you E and N. Okay, we give you my public key and N. And so what you need to decrypt is to find D. You already know, so the private key would be D and N. Now here's the thing. You already know N. But to figure out what D is, you got to figure out that E was, all you know is that E is co-prime to the totient of N. And the totient of N is all the numbers less than N. So you know, so good luck with that. It was co-prime with all those numbers. And it was generated by doing, sorry, no, you don't know that. We don't know what totient of N is, sorry, because totient of N is not prime. But totient of N is a very big number, and if those things are very big, the totient of N is also very big. Okay, very, very, very big. And you'd have to work through all of those examples to try to decrypt it. And if those numbers are very big, then it's theoretically implausible to kind of compute that without knowing it. Because the other thing is that you have to compute this D. All right. You have to compute the D such that E times D is congruent to mod of the totient. It's a lot to compute. Okay, it is computationally intractable to compute these. Right? Basically what we're saying is that you can check all the possible values of x. Okay? So here's the thing. All you have to check, though, that you've got the correct answer, that you've got the correct plain text, is by trying every single value of x for this. Because you can't work it the other way around. Because then you're generating it, because then essentially without knowing what the message is, you don't know which of those possible D's is correct. So the only way to do this is to try x for everything. And e to the, there's a lot of them to try. It takes exponential time. Anyway, so that is why RSA is so let's go ahead and actually see this in action for an actual kind of encryption. All right. So let's go ahead and choose two prime numbers. I'm going to do what the book's doing, which is we're going to choose P is equal to 5, Q is equal to 11, okay? So that makes N what?
4 into 1040?
No, N, not totient of N. Yep, N is equal to 55, okay? Totient of N, also known as, and this again symbol is phi, is equal to 40, as you were saying. Yeah, you just skipped ahead, that was all. 40. Totient of N?
Yeah. What is the meaning?
That means that these are the number of items that are co-prime with 55. The number of items that are co-prime with 55. And normally I'd have to go through and count them. But because I know P and Q, It can do some fancy math. Basically, the fancy math works out. Your book doesn't even mention Toshin Tven, but it's just useful to know that the Toshin exists. That's what it's going to be called and why you're going to see it. If you look online, I just figured that since you might go to online resources, it's worthwhile to know that this exists. Okay. Next. Okay. Next, what we need to do is we need to calculate the GCD of, we need to choose an E, okay? We need to choose an E such that E is co-prime with the Toshin Tven, so GCD of E and 40 is equal to 1. Okay, and the easiest way to do that for me is, I can just run the extended Euclidean algorithm on that, but it's basically we just need to see that E and some number are co-prime. I'm going to choose 3. It's very easy to see that, just for the sake of argument, over here, I'm going to let E be equal to 3, okay? Just for simplicity's sake. Right, we can see that the greatest common divisor of E and 40 is 1. Sorry, of 3 and 40 is 1. So it feels like I can decrypt the thing. Now we need to compute D, which is equal to the modular inverse, right? And if you run through the greatest the extended Euclidean algorithm, we'll find that D is equal to 27. Okay? If you run through this. So now we have E and D. I promise I'll go ahead and do this in a format that makes more sense for us. Code. Okay? So now, let's go ahead. And so now if I want to send a message, let's go ahead and assume let's go ahead and say my message is equivalent to 13. Let's just say that's the message I'm sending, okay? What I need to do is to send somebody a message, would compute 13 to the third mod 40. So 13 to the third, sorry, not mod 40, mod n 55, our original. Okay.
I'm sorry, can you repeat what 13 is again?
Sorry?
What is 13 again?
13?
Yeah.
13 is just the arbitrary message I chose. We can choose anything else, but I chose 13. 13 raised to the third power, mod 55. So unfortunately, that's not. Let's go ahead and do. So what is 13 times 13? That would be
169.
169. Yeah. So 169 mod 50. It gives me what the answer is in the book. I'm just going to skip ahead and use that because, okay, I promise I'm going to give you some nicer ones to do. That is congruent to 13 is congruent to 52. Okay? So that is the encrypted message I would send. I would send the encrypted message for 52. Okay? Now, that's how a message that was encrypted. If 13, if it was sent to me by using my public key, I would get 52. Now to decrypt that 52, I would do 52 to my private key, which is 27 mod 55, and the math works out that this is that actually turns out to be 13, which is the message we originally sent. Of course, I'm just doing this in front of you by scratching on a screen, so let's go ahead and actually code this sucker up. Okay? Let's go ahead and actually see this in action. Now, on your homework, you do run through this algorithm, and again, the videos that I linked, pretty darn good explanations of RSA. Okay, so this is what I coded up earlier. I'm going to go ahead and, though, code it from scratch, but I'll keep this up as a reference in case I mess up somewhere, because I had unlimited time to code that up earlier. And let's see, did I use math anywhere? I did not. I coded everything by hand. Okay, so we computed that extended Euclidean algorithm for a reason, because we need it for both the GCD and we need it for the modular inverse. So what we need to do is we need to generate some keys. Def gen keys. So given P and Q, which are prime numbers, I'm not going to enforce whether or not they're primes. I'm just going to assume I get past two prime numbers, P and Q. So I'm going to now generate my keys for those. Okay? So N, so following the algorithm, N is equal to P times Q. We now generate the totient of N, which is what we call phi. That's the symbol we use, so I'm going to call it phi, is P minus 1 times Q. Yep, Q minus 1. Okay, now we need to generate our public key and private keys, or get our public keys and private keys. And that is done by, well, I'm going to split that up into a separate function so that it doesn't get so messy. Gen E, nope, E, D, and we're going to pass in, and all we need to do is pass in phi over here. That's the only number we need. Okay? Because what we need to do now for gen E, to generate our E, so first thing we need to do is generate E. To generate E, we need to find a number co-prime with phi. Make sense? So how do I find a number that's co-prime with phi? Well, let's go ahead and for I in range, actually let's call it E. We're going to look at every number from, we're going to look at every E from 2 and up, for E in range 2, and then the highest possible number that could be co-prime with phi is phi minus 1, so this goes up to but does not include phi as a possibility, or phi, or however it's pronounced. I don't know Greek. So for E in range 2 to the phi, I think it's phi. So now what we can do is that we can say if, let's go ahead and get our x, comma, y, comma, d, what? From our extended Euclidean algorithm, right? Our extended Euclidean algorithm, A and B. Okay, so what is A and B in this case? Well, it is E and phi. We're checking, right? We run the extended Euclidean algorithm on E and phi because that's the easiest way for it to check if they're co-prime. And fortunately for us, so E is always going to be less than phi, so technically I should have done, if we want to be more efficient. But honestly, actually, E and phi, that's going to be easier for me to remember. Okay? And this will give us the correct answer because we always, we made sure to swap to handle what if that was the case. Okay, so we generate this, and if if the greatest common denominator is equal to 1, that means those two are co-prime. So that means we found our, we found our that this number, okay, is going to be our encryption key. And X is going to be our decryption key. Let me double check that. Should be the case. That's what I did last time. Yep. D is going to be X is going to be the decryption key, right? Because because X in this case is the modular inverse, right? When we generate the extended Euclidean algorithm, X is the modular inverse of X is the modular inverse of A, Y is the modular inverse of B when we in this entire return thing. Okay. So else I'm going to return -1 because this entire thing is broke somewhere. That's -1. Return -1. That's what happens when you talk and type. Okay, so we generated our keys and return our encryption, our public key, our private key, and N. That's it. That's what we need to do encryption. Okay. Now let's go ahead and def run RSA encrypt. So actually, I'll just call this encrypt. Given E and N, what we do is that we return, given a message M and a public key and R N, we're going to return M raised to the E mod N, and given in decrypt, given our ciphertext, a decryption key, a private key, and N, we return ciphertext D, raised to the dth power, mod N. Okay. So let's go ahead and run this. And so now let's go ahead and run this. So we also need, so the only restriction, so first off, let's go ahead and choose 2 prime numbers. Let's see. So prime numbers. 55 is not prime. 53 I think is prime, right?
Yeah.
And then Q, let's go ahead and choose 13. So I'm going to say, so we're going to go ahead and gen keys of P and Q. That is going to give us let's go ahead and get us our encryption key, our decryption key, and the modular space. Print EDN so that we can see what they are. So that gives us our encryption key of 5, our decryption key of 125, and the space is 689. These are pretty small numbers, right? Let's go ahead and set my message, and I'm going to say my message is equal to 100, okay? So what I'm going to do is I'm going to print, let me go ahead and print what happens when I encrypt our message with E and N. So that will get encrypted into 68. Now if I do decrypt, so the ciphertext is all that, D and N. Oh. Yep. We get 100 back. So I sent a message, and I got it, and I successfully encrypted it, and then decrypted it. Except that these numbers aren't usually that small. These numbers are normally, fairly large prime numbers. And let me tell you, running them on large prime numbers really made my computer want to cry. at least with the way I implemented it, which is probably not optimal. What? Was it's true, but regardless, this is the algorithm, and basically here I know it seems silly to send the message 100, but the entire idea here is that even that strings can be encoded as numbers, right? It's just a sequence of bits, therefore a number. So this operation works there. So that's RSA, and it kind of puts everything together. Now let's go ahead and take a. So what? Any questions on it? I know that was a lot.
No. Pretty good.
All right, so let's take a look at your homework from this. I'll assign more homework later this week. Okay? So let's just take a look at your homework. So here we've just got a random question. We look at the recursive multiplication algorithm, okay, that we talked about. Then the last two are relevant for the quiz. Compute the GCD by factoring and by using Euclid's algorithm. So and question 27 gives you RSA of P, Q, it gives you the N, and it gives you E. So it already tells you E is going to be, it gives you basically everything but the decryption key. And because you've got P and Q, and you can figure out what the totient of N is supposed to be. Okay. What value of D should be used for the secret key? Okay. So, and then how do you encrypt it? Or then what is the encryption of 41? So you can run that second part of the question without the secret key, without the decryption key. But for this, you'd need to, run through Euclid's extended algorithm to generate the modular inverse. So this one is definitely good practice for the one on, for a quiz. So what kind of questions should you expect to go over for a quiz? And again, you can bring in a sheet, some notes. Okay. Something with where we do modular exponentiation. So I'll probably give you a question or two, and Fermat's last theorem is probably a little theorem is probably going to come up with that. Okay. A question on doing Euclid's extended, the Euclid extended algorithm, and a question on RSA. Okay. So in other words, the stuff we just did, and two questions that we just did in this first quiz. So I'll be sure to check you off for this quiz, by the way, give you full credit on it because we did work on everything in class together. And again, the quiz shouldn't take that long. If it does, then I messed up somewhere, and so don't fret too much about it. Again, I'm trying to do some low stakes one before we get to a midterm or something like that.
Professor,
Mm-hmm.
when it comes to the algorithms and the quiz, we won't be able to see the algorithm, right? We have to remember them.
You can bring a sheet of notes with you.
Like a sheet, so we put the algorithm on. The
Yes.
quiz. Okay. Okay,
Yes.
I thought by notes you meant scribble paper basically.
No, you can bring a cheat sheet with you. Okay, because that's gonna help you there. For the ones that once we get to once we do the midterm, that's gonna be a bit more. Honestly, I memorizing everything, that's memorization. It's the skill you can develop, and doesn't really test understanding or other things like that. Okay. So what are we going to do so let's talk about, so with that out of the way, let's talk about chapter 2. So chapter 2, I'm just going to give you a brief, quick overview of what we're going to talk about with chapter 2. Chapter 2 has a lot of stuff in it. Where is the slides for chapter 2? Oh, divide and conquer. There it is. So chapter 2 is all about divide and conquer algorithms. What we're going to be talking about is that we're going to review merge sort. Okay? And what we're going to do, we're going to review merge sort and use that to generate the runtime of it. Specifically, the way we'll see that the runtime of merge sort is recursive. It's specifically going to be, the runtime for merge sort will be T of n is equal to 2 T of n plus O of n. Okay? And what we'll learn is that there's something called the 2T of n, 2T of n for 2. And there's something we use called the master theorem that says anything that's in this recurrence relationship, that looks like this recurrence relationship, where we've got where we've got the problem being subdivided into subproblems, we can figure out its runtime by using something called the master theorem, which says that for anything of this format, where we use this divide and conquer kind of strategy, where we take a look at A, B, and the degree of the n in there. Where are you? There. What is a no? Master theorem. There we go. So, why do they sum it like this? This is a much better algorithm. No, that's not even what you have in the textbook. The textbook does such a nice, clean way of doing. The textbook has a much cleaner way of showing it. I don't know why the slides go into it that way. Here's how it looks like in your textbook. We've got any recurrence can be put into this general form. Sorry, divide and conquer looks like this. Okay, T of n is equal to A T of n over B plus O of n to the dth power. We'll discuss what A, B, and D are, but those are the values we care about, A, B, and D. And it says that basically that the T of n can then be translated into one of three possible runtimes. O of n to the dth, O of n to the d log n, or O of n to the log b sub a. Why those runtimes? Well, for the first part, it's kind of simple. For this first one, that's actually fairly simple to figure out, which is that if your total runtime is O to the n to the dth, that means that solving these subproblems really don't matter. This middle case essentially means, if I'm remembering this correctly, because again I have to review this, means that essentially that we kind of are that these two things are kind of balanced. And the last one means that we're all focused on doing the subproblems. Okay, and we'll figure out what those conditions are. Okay, and then we'll see this for a bunch of. Once we know this, we'll take a look at integer multiplication. We'll see that we can actually do integer multiplication fast, a lot faster, by using something called the Karatsuba trick, which basically reduces the number of operations we have to do. And what we'll see is that actually people have been slowly reducing this runtime for multiplication. Okay. Your book briefly goes over matrix multiplication, and it will give an example, but I'm not going to give it. But it uses a lot of tricks. Oh yeah, here it talks about it. You can do a lot of multiplications using. You can. Matrix multiplication, somebody figured out some weird cheat for it to do for combinations of splitting it up into blocks. But again, matrix multiplication also is kind of a race to the bottom. It's somewhere less than n to the third power, but we're not sure quite where it is. But the most important probably algorithm that we're going to go over is something called quick select, which sounds a lot like quick sort, doesn't it? Which is given n elements, find the kth smallest element. So given an array of elements, find the kth smallest in it. And it works pretty well. So there's a lot of but here the idea is that we shouldn't be too worried about recursive algorithms. They're not something to be scared of, because we can now figure out the runtime from them by using this divide and conquer strategy. Okay, so let's see. We end at 420 or 425? Let me check. I plugged it into my phone. 40. It's 435. Okay. So no, it's fine. All right. So let's go ahead and get this started. No time like the present. Merge sort. Okay. We all learned about merge sort, right? Okay. So what we're going to be talking, so as I mentioned, this chapter is all about divide and conquer. I never actually defined that because I figured I'd be defining it on Thursday. Divide and conquer says we take a problem and we split it up into multiple sub-problems which are then solved recursively. Basically, quicksort and merge sort are iconic problems because the idea of quicksort's even easier to see. It's basically says move everything less than pivot to the right, everything greater than pivot goes to the left, and recursively solve those by quick sorting, right? That's how divide and conquer works. Okay. And then once you've got these solutions, combine it to get, so you do those small subproblems to the point where they become easy, and then you combine them into an overall solution. Typically what happens is that the most typical case is that we take a solution. I keep trying to use the pen, but it doesn't work. Okay, we keep taking something of size n and we split it in half, right? N gets split into half into n over 2 and n over 2, okay? So in other words, and then that will happen recursively. So we're gonna have how many splits total? That would be log of n splits, right? For sake of argument, let's assume n is a power of 2 because that makes our analysis nice and easy. So if each of these keeps splitting and splitting until we get to an element of size 1, you're going to have log n splits total, log n layers. Okay. Then you solve those. So once we get down, we can then combine each solution we have a linear time recombination of these solutions. This is the typical way we solve these recurrences. The idea here is that we're going to take something that takes brute force time to solve, ov n squared time, and by using divide and conquer, it's going to become an n log n. So, for instance, insertion sort, which is O of n squared, into divide and conquer, which is n log n. So, given a list of n items from a totally ordered universe, rearrange them in ascending order. Oh man, they use a heavy math term there, totally ordered. That means that basically for any pairs of for any set of items, we can sort them. Essentially, there's a definitive ordering where something is unambiguously the smallest item, something is unambiguously the second smallest, unambiguously the third smallest, and so on and so forth. For all distinct items, right? If two items are the same, that is the only time when it would be ambiguous what order they should go in, right? Like if I've got, if I give you this to sort 3, 2, 2, and 6, right? The output should be 2, 2, 3, 6. But which two should go first? Should it be the first 2, 2 naught, or the second 2? And the answer is, of course, they're twos. We don't freaking care, right? We don't care. They're twos. Now, for an algorithm, for some items like cards that have suits attached to them, or some other more complex objects, things that have the same value might be distinct, and we might care about which order they come in. And sorting algorithms that do care about that, we refer to them as stable sorting algorithms. Those are algorithms that will maintain that order. Okay? We care about that for some cases, and we don't care about that for some others. Did you go over stable sorting algorithms, that term at all? Stable sorting algorithms? No? It's kind of neat. It's kind of niche. Insertion sort is stable. That's why I like insertion. Insertion sort, despite having an O of n squared time, is actually pretty cool because of how well it works in a lot of edge case scenarios. When it's small, it works quickly. When there's only one item out of order, it takes only linear time to sort stuff. So it has a lot of nice scenarios which makes it useful even when we've got these faster algorithms. Okay, sorting out applications, display page rank, list news items in chronological order. Some problems become easier once elements are sorted. That's a good point there. For instance, one easy way to tell if two things are permutations, if you don't want to use a hash map, is you just sort them. And two things that are sorted in the same, that if they're two different things, but you sort them and they become the same thing, then they're permutations of each other. Duplicates, removing duplicates. Very easy to tell what things are duplicate when things are sorted. Because duplicate items show up right next to each other, right? Non-obvious applications, which we'll get into later, are minimum spanning trees. But also, binary search becomes a lot easier once something is sorted. In fact, that's the reason trees work. It keeps everything in kind of a sorted order, which is why we're able to go through it and use binary trees so efficiently. Okay, so merge sort says, hey, recursively sort the left half, recursively sort the right half, and then merge the two results together. Merge sort relies on the fact that relies on that last part, that recursively sorting things together is actually pretty cheap. Specifically, so this is let me go back and do that rundown of merge sort, okay? Which is a bit bigger. Merge sort relies on a hack that if you give that merging A and B, where A and B are two sorted lists, okay? This is hack number one. A and B are two sorted lists, okay? And they're both O of n size, okay? They both have n items. Then that takes O of n time to merge two sorted lists, okay? Let me kind of give you an example of how that algorithm looks, right? You probably went over it, but I'll go ahead and review it since we're getting close to end. So if I've got 1, 3, 7, and 8, and I've got 2, 4, 5, 6 over here, the way we merge things together is I take a look at the smallest item in each of them. And just keep choosing the smallest to put into my new merged list. So 3 and 4. Okay. And now 4 is less than 7, 5 is less than 7, 6 is less than 7, and now we move everything else 7, 8. Notice that I did n comparisons where n is the total number of items. It's linear. That's hack number 1. Hack number 2 that merge sort relies off of. It does have a second hack, which is that this is a sorted list. And this is a sorted list, and they can both be merged together to create a sorted list. In other words, things of size 1 are sorted. So once we get to a base case, we can, of size is equal to 1, it's sorted. So we can merge our sorted list together. So that is how merge sort works. Basically, it says, hey, what I'm going to do is you should merge sort the left to get S left, to get the sorted left. Get your sorted right by merge sorting your right side. And this is like very rough pseudocode because I'm not even like introducing the base case of when you stop doing the recursion. But the point is that and then the point is to just kind of review it. S left, the sorted left side, and the sorted right side go together. Right? So I suppose we can add in our base case, which is that, if our input list is, let's see, if the size of the input list is less than or equal to 1, then it's sorted and we can return it. And otherwise, we do this otherwise we go through this merge sort nonsense and we say, and then we can return this. I know it's a bit of a mess. I'll go again. I just wanted, but you covered merge sort, right? Now, realistically, these days, merge sort is not actually used in your libraries. And actually, one of my unique homework questions will actually be addressing this. Instead, what is used today is timsort, which we will not cover. But timsort is a combination of merge sort and insertion sort. And it does really well on real world data. It basically gets the benefits of both. Because merge sort is always n log n. Always. It's big theta log n. Best case performance, big omega n log n. Worst case performance, n log n. It's always n log n. Here it says a natural variant. Ignore that for right now. Okay? The idea here is, though, that best case performance is O of n. It doesn't even need like any variant or any special thing applied to it. So that's why it's used there. It's used to, but if we look at the Java collection library, okay, and I'll post these later this week, Java collections library, okay, which is, we've got, you should have two sorted, let's see, come on, where's sort? No, is it list that we need to do? Yeah, here we go. So, where is, I think actually it'll be arrays sort Java. Here we go. So, okay. So given a, so here, first off, Java has two sorting algorithms that basically, we can roughly divide it into using two sorting algorithms. First, it uses timsort for objects. Why? Because it's guaranteed to be stabled. The equal elements will not be reordered as the result of the sort. For primitives, for sorting primitives, let's see, dual, like here, if we're sorting integers, it uses something else. It uses quicksort, but not just quicksort. It uses dual pivot quicksort. Okay? So, so I haven't finished writing the homework yet, which is why I haven't posted it.
Or things like quick sort requires a lot of space complexity.
Actually, quicksort can be done in place. Merge sort, it's a bit trickier. So Java uses two algorithms for sorting, timsort and a fancy, and I'll post these, in conjunction with the others, but here's they are to start thinking about them. Just in case you didn't have a lot of other work from all your other classes. So timsort, a fancy version of marriage sort and insertion sort, and quicksort. Why does it have two different sorting algorithms? And then Java uses an implementation of quicksort called dual pivot quicksort. Without looking it up, hypothesize how it works and hypothesize why you would have two pivots. Without looking it up, hypothesize how an implementation of it works. You're allowed to be wrong, so don't look it up. Just start thinking about it and hypothesize. And then for the third question of that one, look up how it works and explain in 4 sentences or less how it works. So that's more of a research question than anything else. Let's try to get you thinking about these things. Okay.